Okay, now we're going to talk about heat capacity. And this is a little bit different from when we talked about specific heat in an earlier chapter. And let's try to differentiate between what is specific heat and what is molar specific heat. Okay, we define molar specific heat. Okay, in this case, we're doing it at constant volume, which means that we're changing the temperature of a gas, but we're keeping it in a container, which is constant. This is going to be different from at constant pressure, which we'll talk about later on, because there we allow the gas to expand and do work as it expands. So that gets a little bit more complicated, and that is what we call CP. So a little bit different from what we have here. But the molar specific heat is different from the specific heat we talked about earlier. Earlier, we defined a constant C for a particular material. We said C is equal to Q, the heat that we add, divided by the mass over the change in temperature. Okay? This one replaces mass with moles. Okay? Different gases will have different molar masses. So your specific heat is not necessarily the same thing as the molar specific heat. Okay, this is looking at energy per mole per degree Celsius or per degree Kelvin. Previously, we looked at energy per kilogram degree Celsius. So molar specific heat is defined by this. And if we write out an equation for heat as a function of the change in temperature with this molar specific heat, it would look like this. So we're really multiplying the molar specific heat times the number of moles to relate energy and change in temperature. Okay, so let's look at how an ideal gas will actually store energy. If we think about this, for an ideal gas, the internal energy, okay, and I have to apologize because we're using U again, and U has been used as potential energy before. We're using it again. Now it becomes internal energy. Wish they would differentiate a little bit better. But here, internal energy is the energy, the thermal energy contained within a system. And for an ideal gas, we don't consider, any of the, potential energy. Now we're using that again, potential energy, to the bonding and things like that. There's no bonding that goes on. There's no intermolecular forces in this approximation of an ideal gas. So for an ideal gas, it's only a function of temperature. We're only putting energy in there by giving the molecules more kinetic energy. So for a monatomic gas, what we find is that the internal energy of the system is equal to 3/2. There should be an N there. I don't know why there isn't an N. 3/2 N RT. And for a diatomic gas, we'll see why in a second, it becomes 5/2 N RT. And again, you need that N there because obviously with more molecules, you'll get more energy. So if we look at the molar specific heat, again, U is equal to 3/2 nRT. If we look at the molar specific heat, a constant volume for a monatomic gas is 3/2 R, okay? 3/2 times the gas constant if we're using N. For a diatomic gas, it's actually 5/2 R. And the reason for this is a diatomic gas has the ability to store energy into different modes. essentially, if we look at, these different modes, we can see that, once again, we have a monatomic gas. It can move in 3 dimensions. And that's basically why we came up with this 3/2 R for the molar specific heat. Again, the internal energy being equal to 3/2 nRT. Okay. For our diatomic molecule, it can actually have 5 degrees of freedom where it can store the energy. Okay. So if this is 3/2 R for our molar specific heat, one would imagine with 2 extra modes where we can store the energy, and we know that for rotational kinetic energy, it's 1/2 I omega squared. With 2 more places that we can store that energy, it's not surprising we're up to 5/2 R. Okay. Again, for our molar specific heat. If we get to more complex molecules, we can actually have even a larger molar specific heat. So generally, the way these molecules can store energy as internal energy really affects their specific heat. Okay. Now, it gets even worse. For diatomic molecules, at a low enough temperature, all of these energies, the rotational energy, okay, is actually quantized. That at its lowest state, it's not rotating. That it can't just start rotating slowly and speed up more and more. Quantum mechanics means that it's at the lowest state where it's not rotating. It's at the next state, which rotating at 1 speed. The next state is twice the amount of angular momentum, and then the third state's 3 times. So if we cool the molecules down low enough, they're not rotating. So therefore, they can't store the energy in terms of rotational speed. So the diatomic molecules at a low enough temperature will behave like a monatomic gas. Okay, they can only store energy in terms of translational motion. But as soon as we go past this temperature, T rotational, okay, half the molecules are now in that next state. And you can see that the molar specific heat here begins to go from this 3/2 to 5/2 until, again, it reaches a state right here. At an even higher temperature, then we have to take into account that the diatomic gas, okay, can start vibrating and store energy in 2 vibrational modes. Okay, and that brings it up to 7/2 RT. Well, the fact of the matter is, for a diatomic gas, normally we just use 5/2. And the reason for this is that the temperature at which rotational modes become important is actually kind of low. So unless you really super chill that gas, it's not going to behave like a monatomic gas. At 20 degrees Celsius, we can pretty much use that 5/2 RT. Okay, like air, you'd have to cool it down to like 2 or 3 degrees Kelvin to get those rotational modes to quit. Hydrogen, 85 degrees Kelvin is a really low temperature. It's right around the temperature of liquid nitrogen. So in all practical applications, as far as we're concerned, okay, these temperatures are so low that that specific heat is going to be, for that diatomic gas, it's going to be 5/2 R. Okay. Now, if you heat a gas high enough, then we have to consider vibrational modes. But look at these temperatures at which the vibrational modes kick in. Okay, for air, you'd have to heat it up to a ridiculous 2,256 degrees Kelvin, and I'm not sure that that gas would even, not disassociate at that level. So, in most circumstances, iodine is an exception. Potassium 2 is diatomic potassium. Who has that as a vapor? Those vibrational modes become significant. So again, going back, in most cases, for the molar specific heat, a monatomic gas is going to be 3/2 R. There's no vibrational modes because there's just one molecule sitting there. For diatomic, yes, theoretically, if we're at a high enough temperature, CV would be 7/2 R. But for practical purposes, this is where we are. And generally, our molar specific heat is going to be the degrees of freedom which are available to us at those particular energies divided by 2 times R. And looking at different gases, let's take a look at this. Looking at different gases, again, we're looking at CV. CP is something we're going to talk about later on, because CP says, what is our specific heat at constant pressure? If I heat a gas, I want to keep it at constant pressure, I'm making the container get bigger and bigger. So I'm actually storing energy in the form of a change in volume, which is work. So that's always going to be a higher amount. But if we think about this, our gas constant's 8.3, roughly about 8.3. And we say that CV for a monatomic gas should be 3/2 R, or 3/2 times 8.3. So if I take 8 divided by 2, I get 4 times 3, I get around 12. And not surprisingly, that's exactly where I see my specific heat, my molar specific heat. Got to be careful here. Molar specific heat for my monatomic gases. My noble gases like helium, argon, neon, krypton. Krypton starts deviating a little bit. So does neon, because they're slightly larger molecules that have a larger van der Waals force, but not really important. We're pretty close to our expectation right here. Now we do the same thing for diatomic gases. I'm going to say that our CV here should be 5/2 R. Okay, remember, if those vibrational modes were kicking in, it should be 7/2 R. But again, we're going to take about 8 divided by 2. That gives 4. 4 times 5 is 20. And right around 20, a little bit more than 20. And our diatomic gases fit very well in there. So that tells us that, we have the translational modes, which are going. We have the rotational modes that are going, but the vibrational modes don't play a role here. Okay? And obviously with polyatomic gases, our specific heat is going to be even higher because we have even more modes to which we can store the energy. Okay? So you might have seen this in chemistry. And again, molar specific heat's not the same thing as small c that we saw before. Molar specific heat's a big C, in this case, constant volume. Again, if you do the constant pressure, that's a different thing that we would need a totally separate analysis to find. Okay.